guys, welcome to yet another video from the series about statistical sampling, and this time we will talk about Markov chain Monte Carlo sampling or MCMC sampling, which is probably the most buzzwordish method of all sampling methods we have talked about. Before we go in, I hope you are enjoying the series, so let me know in the comments whether we have some topics you would like to cover or discuss, and we can definitely get to it. Alright, so let's go. So some motivation. So far we have talked about three sampling algorithms. Each of them had some pros and some cons. So inverse transform sampling are very fast and reliable, but you have to know the ICDF, the inverse cumulative distribution function. Then the rejection sampling, it's easy to implement, it's easy algorithm, but can be inefficient, especially in high dimensions. And then important sampling, it's like a very cool algorithm, but it's not really algorithm to obtain the samples, the individual points. It's more about improving on the integration and get the summaries of the data. And now the question is, can we figure out or come up with some other approach how to obtain the samples? And the answer is yes. What we will talk about in this video is how to utilize the Markov chains to generate a series of samples from some desired distribution, and we will see whether we do better than some of these methods here. But before we get to it, I want to briefly touch upon this topic of Markov chains. So this is the probability 101, feel free to skip. But what is Markov chain? So the Wikipedia definition is that it's a sequence of possible events in which the probability of each event depends only on the state attained in the previous event. Here we have the mathematical notation, but basically what it says is that what will happen tomorrow only depends on what the state is today and not on the yesterday or some time before. So the typical example we see is this how the weather is changing. So you have two states, it can be either cloudy or sunny, and the probability that it will be sunny tomorrow, if today is sunny, it's this 0.8, and tomorrow that probability that tomorrow will be cloudy given today is sunny, it's like this 0.2. So the transition between the states is given by the arrows, and the probability of it is given by the number at each arrow. So this is what and what's the Markov property of this is that if the weather tomorrow only depends on the weather today. So it doesn't matter if yesterday was cloudy, sunny, or if the sun had some eruptions, whatever. The only thing that matters, what will be the weather tomorrow, is what is the weather today. And so the previous example, it's easy. You have two states, but you can have infinite many states. So here we have another example, which means so probability of xn given xn minus 1 is driven by this normal distribution with the mean equals to x minus 1 and the deviation or the variation is 1. So how does it look like? So let's start. We have this axis, we are in the state 0, and this is our distribution n centered at 0. And now basically if you ask me what's the next state, I will just generate number from this n normal distribution. And let's say that this is what I generated, and now I can, if I want to generate a next state, I will just move there on top of this distribution with the center, the mean of this previously generated sample, and now I can generate a new sample which is the next in the line. So for example, here I generated the sample more near to 0, and then again, if you ask me what's the next sample, I don't care about x1, about 0, I only care about x2. I build this distribution on top of it and I generate a new sample. And I can repeat this over and over and over. And I will get this array of samples or states, basically this chain. So I started at 0 and then I moved to all the way to here x5, but basically this is what the Markov chain is about. And now what the Markov chain Monte Carlo does. Yeah, so suppose that we want to sample from some target distribution Px. This is always the distribution we want to sample from. Yeah, let's assume that we can write it as fx over k, where k is the normalized constant. So fx is basically just a normalized Px. And let's also assume that we are not able to sample directly from Px for whatever reason. So same settings as in the previous problems or previous algorithms, previous videos. And now the idea behind the Markov chain Monte Carlo is to use the Markov process to asymptotically reach the Px. And what does it mean? That we want to generate this array, this list, the sequence of samples from Px, and we want to generate it using the Markov chain approach, and we hope that it will basically represent this Px. And the question, of course, is how to do it. And one way, probably the most glorified algorithm in this MCMC space, is the Metropolis algorithm. Yeah, so how it works? So basically, Metropolis algorithm employs this symmetrical proposal Markovian distribution. Here we denote it by Q of xn given the xn minus 1, from which we are able to sample. So this is the generating or moving distribution, how it's also sometimes called. And now the goal is, let's start at some point x0 and let's generate the samples from this proposal green Q distribution from which we are able to sample. And then the magic is we have to smartly decide if we want to accept this sample or we don't want to accept it. Therefore, if we are stepping in some bad region that is not for us too smart to accept the samples in, we want to stay where we are. So we are forming this path and we are forming it in a way that it should be the most probable under Px. Alright, so this is the formal algorithm of the Metropolis algorithm, and let's see how it actually works in action. So we will maybe get to this algorithm again, but let's just demonstrate it on an example. So what we do have here is, so here on top we have this proposal distribution. Here the yellow line is what we want to sample from, so this is our target distribution, and down here we have this array of samples, and now we want to basically fill out this array with samples that should come from the yellow distribution, but we will be utilizing the green proposal distribution. Okay, so we have to start somewhere. Just choose x0, let's call it, let's assume it's 1, so we will put it into the array of samples, and this is our starting point. And now we will again build this proposal distribution on top of it. So we will we now want to sample x1 given the x0, so this is our distribution from which we will sample. Let's sample, okay. And now we are not accepting this sample yet. We have to decide whether it's smart to accept it. So how is the smartness decided? So basically we assume that the f of x can be evaluated at each point, and therefore we now will look at the values at each of the point of x0 and x, and here we don't denoted it x asterisk, and we will compute the like the fraction between these two. So f of x asterisk over f of x0, and here we see that it's basically higher than 1, and we will then cut it down to 1 as we want this number to be between 0 and 1. And now we want to decide whether it's smart to accept the x asterisk as our next sample on the path. And basically how we do it is that we will generate a randomly uniform number between 0 and 1. And if the alpha is higher than this uniformly distributed number, then we will accept the sample. Otherwise, we will not accept it. The cool thing, and maybe it's also the curse a little, is that if the alpha is 1, then we will always accept the sample. So you can see here a little bit of hint that if you sample, or if the proposal sample has higher probability distribution in terms of the F distribution or P distribution, then it will always be accepted by the Metropolis algorithm. We will see how this will behave in a moment, how pitfalls it can cause. Yeah, but here we basically say, yeah, so the uniformly distributed number, the random number is lower than alpha, therefore we move to the new sample, we accept it, and we move there. So we just make the step on our path. And now we will put it into our sample array. And now we continue. So we are now here, we have this state x1, we are in this number 1.2, and we will do the same thing again. So we will build the proposal distribution, we will propose the sample, and we will again evaluate how smart it is for us to move to the sample. We will do it by evaluating this fraction. We see it's higher than 1, so the alpha is 1, and therefore we will generate this number, but we already know that it's not really necessary, and because it's lower, this uniformly generated number is lower than alpha, we will accept the sample, and we will basically take the step on our path. So yeah, we will move, and we will fill our sample array with a new sample. And now we will do the same thing again. So again, build the proposal distribution, and now we proposed a number or sample by 1.15, and now we have to evaluate how smart it is for us to actually move there. And this is where things get interesting, because suddenly we see that the fraction is lower than 1, and now we are basically playing a Russian roulette of how smart it is to move there. And we will generate this uniformly distributed number, and we will see that this time it's again lower than the alpha. Therefore, it is smart for us in this moment to move into this location. So we basically now played the roulette, and we had this 60% chance that we will move, but we had also like 40% chance that we will stay where we are, because it was not so smart to move there. And we moved into this 1.15. And we will do the same thing again. So again, build a proposal, propose the new sample, and again compare the values. And now we will see that the fraction gives us quite a low number, so 0.4. And now we will play the Russian roulette of smart move again. And now we actually have quite a low probability to move there, so it's just 40%. That's not that low, but definitely before we had 60 and 1 and 100. So we will play the roulette, and suddenly we see that we are not so lucky. Because this randomly generated numbers is higher than the alpha, we will stay at the x3 where we currently are. What does it mean? So we basically say that we at this step we didn't move to the proposed sample, but we basically stayed where we are. Therefore, it's like when we are walking our path, we just didn't move, but we are just now staying at one point. And therefore, the new sample in the array will be when it comes to the value, it will be the same as the previous one. And again, we will again propose some sample. We will again find the value of the fraction. It's now 0.8, and we will play the Russian roulette again. And wow, and this time we got again maybe unlucky, and again it says that we just generated a number that was higher than the alpha, and we will stay where we are. So therefore x5 in this chain, in this sample array or sample list, will be the very same value as before. So we are still staying where we are, because it's not smart for us to move to the proposed like the proposed direction. Okay, so this is how it works. This is what the Metropolis algorithm is about. You will sometimes find in the literature that there is this Metropolis-Hastings variant, which is basically employing a new way of calculating alpha, because it's now allowing you to use non-symmetrical proposal distribution. So if you put this fraction or this extension to the formula, you can also have the Q non-symmetrical. So it can be basically any distribution that you can propose samples from. All right. Yeah, so some of the properties of this MCMC, or in our case the Metropolis-Hastings algorithm, is that the subsequent samples in the chains are inherently autocorrelated. But at the same time, it's true that we want our samples as independent as possible, because then you quite nicely represent the distribution. So that's one interesting property. Another one is that maybe it's not so obvious, but the chain is strongly dependent on the choice of the initial value, and especially the first X or whatever letter samples will be strongly affected by the choice of the initial value. And like you need, in order to reach this stationary distribution, or to cut down on this autocorrelation or this unfortunate or fortunate start, you basically want to minimize dependency on the initial value as much as possible. Yeah, so we call this like this some number of samples where they are strongly dependent, like through the autocorrelation, they are strongly dependent on the initial value. We call it the burn-in period. So this is something that must be tackled. Also, as we already actually saw it, is that the Metropolis algorithm has this tendency to stuck or to move to the local peaks, to the local maximas, and be stuck there. Because when the alpha was equal to 1, we always take the move, and the alpha was always equal to 1 if the proposed distribution, the proposed sample had higher value of the target distribution than the previous one. And last but not least, the choice of the proposal distribution can also impact the efficiency of the algorithm greatly. So these are the properties, and I would even say like maybe pitfalls of the MCMC / the Metropolis-Hastings. But how do we deal with it? So, for example, for the autocorrelation of the samples, there is this technique called thinning, that you only store every mth sample, so every 5th or 10th or 100th sample, and you discard the rest from the chain. So therefore you will reduce the autocorrelation as much as possible. Then there is this burn-in period. So how to deal with it? So basically the solution is simple: discard the first examples. We will zoom on it later why this is even the case. And then the two last properties, this is sometimes referred or connected to the term mixing. And when you are not stacking the chain in local peaks or at some value, and you are basically exploring the whole thing quite nicely, it's called rapid mixing. But when you are getting stuck into this local peaks, and you are not really exploring the distribution, and you are not generating good mirror or good image of the distribution through the samples, it's called poor mixing, and we will again zoom on it later. Okay, so the burn-in period, so what does it mean? So we talked about it a little bit theoretically, but what does it mean in practice? So here we have example, we want to sample from the PX, and we have we are doing the MCMC sampling. Yes, so we choose the X0 and now we are getting the samples, and we are slowly moving through the alpha mechanism on top of the chains, and here we are getting the values. But if you actually draw a histogram, or if you smooth out these samples into this green line, then you basically see that a lot of weight of the sample array, or the sample list, or this sample distribution from the samples, this green distribution, is at the beginning. And why is that? Because this is where we started the chain, and therefore before it even got to these areas of high probability under px, it took some time, and it was stuck here because it's quite a plateauish distribution in this region, so it was stuck there. So what happens when we do the burn, when we discard the burn-in period? Yeah, so let's say that the first 8 samples or 9 samples are in the burn-in zone. So let's just discard them away. And how does it look like now? So now the distribution, the histogram, is much more resembling the target distribution px, and it was just because we discarded this first randomly affected by the initial point choice points that were doing this bump at the beginning of the distribution. So this is the burn-in period. Now the tricky question is, how do I determine the length of the burn-in period? It's not so straightforward to answer. Usually you can look at the distribution of the samples and the values and how it evolves in time. And if you see that the first few samples, the values of the samples are highly not matching the rest of the samples, that's probably the burn-in period. Yeah. So for example, in this picture on the right side, we can see that we started somewhere in here. So the first sample was something about around like 15, and then the next sample and the next sample and the next sample in the array was quite changing, and then after some time, so after like this period, I would say, we are getting quite stable chain. Also, you can do this test not by eye, but you can use some formal test methods such as Givecki test or Heidelberger-Welch test or Rafter-Lewis test, and basically you can compare the means of some number of samples. Yes. So you can take the last x 1000 samples, and you can take the first x 100 samples, and if the mean differs a lot, then it's probably still in the burning zone. But once the mean starts to get we'd say stabilized, it's probably out of the burning zone. So somewhere where this ends is the right way to cut it. Okay, so that was the burn-in, very important thing. Now, chain mixing. We are talking about these traps to the local maxima. So what does it? Why this happens? So we have this px distribution which has multiple peaks, and now I want to do the MCMC, and I start. So I choose some initial value. I will generate the samples, the proposal sample. I will accept it. Again, I will move there, generate proposal sample, accept it, move there, generate sample, and this time I will not accept it. So I will stay where I am, and I will generate a new sample. Again, I won't accept it, and I will stay where I am. And this means that we will basically be stuck in this region, and we will never get through this, I would say, like this power barrier, because we will not be able to have the roulette on our side and get through it. So this is a problem here, because if we do this, it will then look like the px is just this part, and this won't be considered at all. So we are basically stuck. how to deal with it? So one method is to use or start multiple chains at like various locations and sample from all these chains simultaneously. So this is how it would look like. Yeah? So I would sample, I will move the distributions, and I will end up in something like this. And now I can combine the samples together, and this will form. I can say that the samples from this are the representation of the target px distribution of the yellow distribution. Of course, I have to be a little bit careful with the combination, because if these two, for example, overlaps, then I will have maybe a little bit more samples here than I should have, because there is this overlap. So I have to be careful in then discarding or otherwise like adjusting the final sample for these duplications. The next proposal that was given how to tackle this problem is to utilize adaptive proposal. And what does it mean is that you can reduce the variance of the proposal as time goes. So for example, at the start, this is also used by the this approach is used also by the simulated annealing heuristics, which is very cool heuristics. You will start with a very wide variation of the distribution, and then as you go, you will lower the variance, and you will say, oh, I'm more confident that I can accept or generate samples closer to my current state. So I will start with very wide proposal. Let's start here, and let's propose something from this very wide proposal. So I have chance to propose from like this region, and it's quite non-trivial chance. So I proposed this sample, I will move there, and I will slowly lower the variance of the distribution here. And now I will propose a new sample, for example here. I will move there, and notice that the variance of the proposal of the green distribution again is a little bit lower. Yes, so it's the overall it's higher, and I'm getting like more and more less so less and less room where I can sample. So previously I had all this I have all this region. Now I have just this region. And now I will sample again. I will move my proposal there again, lower the variance a little, and I will propose a new sample. I will move the proposal there, and again, okay, so this time I reduce the variance a lot, but I will slowly reduce the variance again. And this is how it works. Yeah? So you can play with the proposal distribution, and you can like adjust it. And if you have if you feel like you are accepting all the same samples again and again, you can maybe increase the variance, and otherwise you can decrease it. Now, how does it manifest there? So this is maybe a little bit complicated graph, but basically what we have, what is this graph telling us? So here, I have my px, it's inverted 90 degrees. So if I rotated it 90 degrees, it would be the same picture as before. And here on the right side, I have this x-axis, which represents, I have the horizontal axis, which represents time or steps. And then I have this vertical axis, which represents the value of the samples proposed. And basically, what I can see is that if this green line have these plateaus, it basically means that it's being stuck at some of the at some region. So it's stuck at this value of x of the proposal samples for some time. And therefore, it's showing that I have some problem with the peaks, or I am getting stuck in the peaks. Whereas here in the bottom, I have this very wide and wild green line, which basically represents that I'm not getting stuck at all, and I am basically sampling from like all parts of the distribution. So I started here, so here it was my first point, and then I quite fastly move into this main area, and now basically I'm sampling. Yeah, so I'm sampling this, I'm sampling this, I'm sampling this, I'm sampling this, sampling this, and I'm basically exploring and exploring the entire distribution, and then I'm being stuck at the most like prominent values. So here, so I stuck here a lot and stuck here a lot. So the top graph usually represents the poor mixing. The bottom one usually represents the rapid mixing. Of course, I have to be careful about the bottom one, because it also can be that I'm just generating complete random numbers. It's like all over the place, so I have to be a little careful how I interpret it. But usually, when you see this, when you see these like long stuck areas, it's sign of a the chain needs some help to combat this. Okay. Yes, so the conclusion, Markov chain Monte Carlo, it utilizes Markov chains for generating samples. It has some issues, we tackle them. It has some solutions to these issues, and overall the Markov chain Monte Carlo is very general, and I would say generally usable algorithm, very versatile. So typically it's employed, it's like the usual choice for sampling using it's basically the most generic and used sampling approach there is, because why is that? Because it works quite nicely in the higher dimensions compared to, for example, rejection sampling. So it's one advantage of the algorithm. And also there is this promise that the MCMC algorithms can be designed in a way that actually very little calibration is needed. So in the rejection sampling, if you don't find the right envelope function, you can really decrease the efficiency of the algorithm a lot, or you can maybe render it quite useless if you choose it very poorly. But in the MCMC, you don't have to deal with it. You have to deal with the burn-in, with the mixing, but it's less hassle than the rejection sampling envelope function at some destinations or some points. It has some disadvantages, of course. This is the autocollated samples. You can't really avoid it, but when you do the thinning, you can like be very reasonable in practice that it's not such a big problem. But the samples are not really like IID, so this is one drawback compared to the rejection sampling. And then, as it was mentioned, taking care of this thinning, burning, mixing, it sounds overwhelming, but it's this triple hustle, but still this can be tackled in quite good way. Okay, I think that's it. So thank you very much. If you have any questions, please comment. If you like the video, please like it, and hopefully next time. See you.